last video, we started step 4, which is extending phi q to the reals. And in order to do this part of the proof, we need a whole lot of new techniques and some properties of Dedekind cuts that I went over last time. So now we're ready to move on to actually proving that phi r, the map that we've defined, which is that phi r of r equals the supermem of phi q of dr, where dr is the set of all q with q less than r. So this is our definition of phi r, the map from x to y. And now we're ready to start actually proving that this map is an isomorphism. And to do that, we need to prove that it's a bijection and then prove that it preserves addition and multiplication. Of course, we also have to prove that it's order preserving, but we're actually going to do that today because one of the observations that I demonstrated last week was that actually if a map is order preserving, then it is one-to-one by definition. So we'll use that fact to prove, we're going to prove that the map is one-to-one by showing that it is order preserving. Okay, so showing that it's a bijection is actually relatively, compared to what's coming, not so difficult. It's still involved, but I think I'm actually gonna split addition and multiplication into 2 more videos. So it'll be 2 more videos after this one. We'll do bijection today, and then addition next time, and then multiplication. So first up is that phi r is well-defined. And well-defined means that x equals y implies that f of x equals f of y. So we showed last time with P2 that r element of x is the least upper bound of dr, which is the set of all q less than r. Oh, and with q, an element of the rationals. So dr is the set of all rationals less than r. And we showed last time that in that case, r is the least upper bound of that set. So what we have to show is that if x equals y, so basically we just assume there's some other number, r prime, element of x, with r equals r prime, and then we're going to show that in that case phi r of r equals phi r of r prime. So let d of r prime be the set of all q less than r prime with q element of qx. So since r equals r, then it has to be that dr equals d r prime. Turn the page. So as we showed before, the set phi of q of dr, which is all of the q's, all of the elements of dr sent to y with phi. This set must have a least upper bound in y, which we set to phi r, right? That's our definition of phi r, is it's the supermem of this set. But since phi q is well defined, then phi q of dr must equal phi q of dr prime, because these 2 sets are the same, so if you take phi q of both of them, they have to be the same as well. So if these are the same, then the supermems must be the same, so phi r of r equals phi r of r prime. So that's what we needed to show. If r equals r prime, then phi r of r equals phi r of r prime. This feels almost like too obvious to state, but the reason is, remember that well-defined means that the function, that it's in fact a function, that it passes the vertical test, so that the function doesn't, or the relation doesn't go like this, where one value of x might have multiple values of y. Well-defined means that each value of x will only have one value of y. So we just had to verify that. Okay, let's start on a new page. That one was easy. So now we're going to show that phi r is order preserving, and thus 1, 2, 1. So we showed in the previous video that if we show it's order preserving, then it follows that it's 1-to-1. So what we need to do is show that r is order preserving. That means that if r is less than s in x, that implies that phi r of r is less than phi r of s in y. This means that it's order preserving. Okay, so assume that r and s are real numbers in X with r less than s. So now we can choose rational numbers p and q such that r is less than p is less than q is less than s. Then all this is two applications of the density of rationals, because we have two real numbers, so we know that there's a rational number in between them. Then you just take these two real numbers and there's another rational in between them. So we can keep doing this forever. So we have the two rational numbers such that r is less than p is less than q is less than s. Now we're just going to look at what we can figure out from this. So step by step, we're going to show that this will imply that this is true. So first we'll just look at this inequality. P is an upper bound of dr, right? Because if dr is all rationals less than r, and p is bigger than that, then obviously everything in dr is going to be less than p as well. So p is an upper bound of r, and phi q is order preserving. So phi q of p is going to be an upper bound, I'll say that's upper bound, for phi q of dr, right? Because if we take every element of dr, apply phi to it, then phi q of p will still be bigger. So phi r of r is defined as the least upper bound of phi q of dr, right? That's the definition of phi r. Therefore, phi r of r is less than or equal to phi q of p, because phi q of p is an upper bound of this set. Phi r of r is the least upper bound of this set. So any other upper bound is going to be bigger than or equal to the least upper bound. So now by P3, we have that phi q of p equals phi r of p, because p is a rational. So we know that the phi q of p equals phi r of p. So therefore, we have that phi r of r is less than or equal to phi r of p. Okay? So we started with r is less than p, and so far we've established that phi r of r is less than or equal to phi r of p. So there's a little bit of problem here because this is less than or equal to, and we started with just less than, but we'll take care of that in a second. So, okay. Next one, we're going to start looking now at p and q. So, again, phi q is order preserving, another abbreviation. So if p is less than q, that implies that phi q of p is less than phi q of q, right? This is what we did with the rationals. We already know this about phi q. In addition, we know from P3 says that phi q of p equals phi r of p, and that phi q of q equals phi r of q, because both of these are rationals. So that means that if phi q of p is less than phi q of q, then just putting these together, we have, therefore, phi r of p is less than phi r of q, right? So this is the second step, and notice here we preserve the strict inequality. So this is the key point here. This is why we needed the 2, because we can show that phi r of p is strictly less than phi r of q, and then even if the other sides are equal, this forces the one to be less than the other, which is the last step. So the last step here, we have that r is less than p is less than q is less than s. The last step here is to examine q is less than s. So since q is an element of the rationals in X and q is less than s, then q has to be an element of ds, right? This is just a different set with the same thing. ds would mean all the rationals less than s. So again, since phi q is order preserving, then for the same reason we just said, phi q of q is going to be an element of phi q of ds. We just did that same thing for P. Now, we know that phi r of s is the least upper bound of phi q of ds, right? So if phi q of q is an element of this set, and phi r of s is the least upper bound, then phi q of q must be less than or equal to phi r of s. But furthermore, since q is rational, we know that phi q of q equals phi r of q. Therefore, putting these together, we have that phi r of q is less than or equal to phi r of s. So putting all of these inequalities that we've established together, we have, first we show that phi r of r is less than or equal to phi r of p. Then we show that that is strictly less than phi r q, and that that's less than or equal to phi r of s. So if you put all these together, that implies that phi r of r is strictly less than phi r of s. So therefore, r less than s implies that phi r of r is less than phi r of s, and that's what we wanted to prove. So phi r is indeed order preserving, and by observation 8 from the last video, therefore phi r is 1, 2, 1. Okay, good. Finally, so we've shown it's well defined, we've shown it's 1 to 1. Last thing is show phi r is onto. Now, onto means that for each y in y, there exists an x in x such that phi r of x equals y, right? That's the definition of onto. It means that y is covered by the x's, that there's some element of x that will give you each element of y. So let y be arbitrary. Now we're going to have to do something a little different. So let d star of y be the set of all rational numbers in y such that q is less than y. So it's the same definition as d of y would be, but we're in y now instead of x. So P2 tells us that y is the least upper bound of this set, right? Y is the least upper bound of d star y. So observation 7 told us that since phi q is 1 to 1 and onto, then phi q, then the inverse of phi q exists also. So we're going to be looking at this. So what we're going to do is we're going to be taking this set in y and using the inverse of phi q to send it to x, and then looking at that and then going back to y. So what we need to do now is to define this. We're looking for this number that phi r will send to y. So as before, there exists a k, an integer k, which is in the integers in y, such that y is less than k. Okay, so it's bigger than k. Therefore, k is an upper bound of d star y, right? This is the same thing we did before. If there's some integer that's bigger than the least upper bound, then it's going to be an upper bound of d star y. So therefore, since phi q is order preserving, so is the inverse. So the inverse of phi q is order preserving. So it follows that the inverse of phi q of k is an upper bound of the set, the inverse of phi q of d star y. So what we're talking about here is we started in this case, we have y and we have x. So we started with some number y. We defined the Dedekind cut d star y, right? Then we used the inverse of q to send everything down here. So now we have a set here which is the inverse of phi q of y, which has something here, and then it's everything over here. So what we did is because the inverse is order preserving, that means that the inverse of phi q of k is going to be an upper bound of this set. So that means now that that phi q inverse of k is up here somewhere. It's bigger than everything in this set, so it's an upper bound of this set. Now, since this set has an upper bound, it has a least upper bound. That's the least upper bound property. So we're going to call that least upper bound, we're going to call that x. So let x equal the supremum of the inverse of phi q of the set d star of y. Okay? Looks ugly, especially when I'm not even writing it well. Okay. Now, what we have to do is show that if you take phi r of x, it equals the original y, which we started as arbitrary. This y can be any element of the set y. And if you take this, if you set x to be the supremum of this set, then you take phi r of that number and you'll get y in return. That will show that phi r is on 2. Okay. So we need to show that phi r of x equals y. So first we'll show that phi r of x is an upper bound of d star y, then that it is the least upper bound. So let q be an element in the rationals in y such that q is less than y. Then choose a rational p such that q is less than p is less than y. Let qx equal the inverse phi q of q. So we're just going to denote this number. You basically take phi q, send it back to x, and we'll denote that as qx. And same with px equals phi q inverse p. Now phi q inverse is order preserving, so q of x is less than p of x, right? So we started with q is less than p, so if you move them to x, q of x is less than p of x. P and q are elements of d star y, so px and qx have to be elements of the inverse set in x. Now, we defined x as the least upper bound of this set. So x is an upper bound of this set. So it has to be that qx is less than px is less than x. So now we just finished showing that phi r is order preserving. So if we have this relation in x, then we just showed that therefore phi r of qx is less than phi r of px is less than phi r of x, right? If this is true, then this is true, because we just showed that phi r is order preserving. So the definition of an inverse function says that if px equals the inverse of phi of p, then that implies that p equals phi q of px. This is just, you're just flipping it from one to the other. If you take phi q of both sides, then p equals phi q of px. Same thing is true of qx. So qx implies that q equals phi q of qx. And now, using p3, because px and qx are rational, then this equals phi r of px, and this equals phi r of qx. Right? So we just finished showing that phi r of qx is less than phi r of px is less than phi r of x. So with these two equalities, that implies that phi r of qx equals q, phi r of px equals p, and these are both less than phi r of x. So finally, since q and p, we started by choosing q and p to be elements of d star y, because q is a rational number less than y, and then p is also a rational number less than y. So p and q are elements of d star y, and they're both less than phi r of x. That means that phi r of x is an upper bound of d star y, right? So that's a good first step. So we've shown that phi r of x is an upper bound. What remains is to show that phi r x is the least upper bound of d star y. So we know already from P2 that says that y is the least upper bound of d star y. We just showed that phi r of x is an upper bound of d star y. So that means that y has to be less than this, because this is the least upper bound, this is some other upper bound, so therefore y is less than or equal to phi r of x. So now we just have to show that in fact y is not less than phi r of x, it is in fact equal to. And that is technique 2. If y is less than or equal to phi r of x, but y is not less than phi r of x, then y must be equal to phi r of x. So what we have to show now is that y is not less than phi r of x. How do we do that? We assume the opposite. So assume that y is less than phi r of x. Now we're going to show that this leads to a contradiction, and therefore this must not be true. Therefore, y equals phi r of x. So if this is true, then there exists q in the rationals in y such that y is less than q is less than qr of x, or phi r of x, because the rationals are dense in y. So now what we're going to do is show that, in fact, q is an element of d star y, which means it has to be less than y, so our assumption must be wrong. Okay, so q equals phi q of qx for some qx in the rationals in x, because phi q is onto and q is rational, and therefore we know from P3 that phi q of qx equals phi r of qx, right? That means that q equals phi r of qx, so that means that phi r of qx is less than phi r of x, because that's the definition of q, and q equals phi r, so this implies this. But we've shown that phi r is order preserving. That's what we did when we showed that it was 1-to-1. So this must imply that qx is less than x. Because if this is not true, then this wouldn't be true, because if you apply phi r to both sides, the order is preserved. So therefore, phi q is less than x. Now, the thing is, x is the least upper bound of the inverse of d star y. This is how we defined x, as the least upper bound of this set. So that means that, so remember, all of this is in x. X is in capital X. Qx is in capital X. This whole set is in capital X, because phi q, the inverse of phi q, sends everything in y to elements of x. So if x is the least upper bound of this set, that means that qx has to be an element of this. So therefore qx is an element of phi q inverse d star y. So we already showed that phi q of qx equals q. And we know that phi q is order preserving. So that means that if we send all of this back to y, we must have that q, which equals phi q of qx, must be an element of dy, d star y. Because if qx is an element of the inverse, then that means that qx is less than phi q inverse of y, right? That's what it means to be in this set. So if qx is less than that, then if you take phi q of both sides, you're going to get that phi q of qx is an element of d star y, and that's what q equals. So q then is an element of d star y. Therefore, q is less than y, right? Because we just showed that q is an element of d star y. That means that q is less than y. But we started by assuming, we defined q to be greater than y. We started by assuming that y is greater than q, or that y is less than q. Starting with that assumption, we just came to the conclusion that q is less than y. That's a contradiction. That means that our assumption had to be wrong. That means that y is not less than phi r of q, which means that y is not less than phi r of x. Sorry, the y is not less than phi r of x. That means that y equals phi r x. So therefore, y equals phi r x. And that is what we were trying to prove. So what we just showed is that phi r is indeed onto, because for any arbitrary element of y, there exists an x such that phi r of x equals y. That means that phi r is onto. And namely, that x is the supremum of phi q of minus 1 d star y. You apply phi r to this, and you get y. So phi r is onto. So that's it. We've shown that phi r is well-defined. We showed that it's order-preserving. We showed that it's one-to-one. And now we showed that it's onto. Next video, we'll show that it preserves addition. The next video will show that it preserves multiplication. Those are both very hard proofs. And then we'll be done with this. One last step then, which is to show that, in fact, there's only one such map that maps x to y, which means that not only is there an isomorphism between these two sets, but that the two sets are in fact the same set, that real numbers are rigid, and the only isomorphism is the identity automorphism. Okay, see you next week.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.